Eisenbud is a world-leading mathematician from the United States whose work has shaped modern commutative algebra and algebraic geometry. A professor at the University of California at Berkeley, he's also a former longtime director of the now called Simonds-Laufer Mathematical Sciences Institute, where he played a central role in expanding programs, outreach, and the Institute's global impact. He was also president of the American Mathematical Society. Eisenbud's research centers on syzygies, free resolutions, and the homological ideas that connect algebra to geometry. His outstanding results have become standard tools in the field. He has also been a strong proponent of computational approaches contributing to early developments in computer algebra systems. He's an author of widely used graduate texts such as Commutative Algebra with a View Toward Algebraic Geometry and The Geometry of Syzygies, which have educated generations of mathematicians. In particular, his book with Walter Neumann is a Bible for people like me working on the topology of singularities. David Eisenbud's blend of deep research, clear exposition, and institution building has had a lasting impact on the mathematical community. It is a privilege to have him with us in Cuernavaca, and this is being possible thanks to the support of the Simons Foundation. David, thanks for being here, and welcome to Mexico.
Thank you. Thanks for that nice introduction, too. So I want to give a talk which combines actually many of the themes that Pepe mentioned, and starts with really a little bit of history and of the theory of algebraic curves. So there's a vague approximation to a plane quartic algebraic curve, or at least the real points of it. You can see that it's degree 4 because if I draw a line in the plane, typical line meets it in 4 points. So that is an equation of degree 4. If I restrict it to the line, you see the equation of this. Of course, I get a quartic polynomial with 4 roots. And there are lots of other lines that don't seem to meet at the right number of points, either because I drew badly or because the other points are complex. If we could draw in the complex plane, we'd see them all. But really the theory of curves and such things in the 19th century, for the first half of the 19th century, concerned things like this, real plane curves. We had all the ingredients for complex projective curves. Gauss had proved the fundamental theorem of algebra, finally around 1800. The people began to develop projective methods in the first half, but still this was the dominant subject in algebraic geometry at that time, until Riemann. And in 1857, Riemann really changed the field completely by focusing on the function theory instead. Now this was the union of 2 streams of work, really. People had been very interested in integrating funny differentials for a long time. The theory of elliptic integrals was a big deal earlier than this. And Riemann also focused on differentials. But he basically studied the function theory on any sort of surface. And his surfaces typically were coverings of the Riemann sphere. So that what we would now consider Riemann surfaces. So this changed the field, and he proved remarkable inequality, which said something about the number of functions of a certain kind, which I'll tell you in a moment. It was completed by his student Roch a few years later in the Riemann-Roch theorem. But though we think of it as sort of, Riemann came, he did that, that's done. But in fact, the proof was based on a use of the Dirichlet principle, which says that if you have a bunch of functions and some functional on that and a lower bound. They're all above it, but they approach the lower bound, then you can find one that reaches the lower bound, which is true sometimes and not other times. And Riemann tried to prove the Dirichlet principle in the case he used it and failed. It was disputed by Prim a few years later and definitively shown that his proof was wrong. So people didn't believe the work that he had done, and Klebsch set out to reclaim the work in terms of algebra. So algebra is this thing, right? If you have a plane curve, you have one function of two variables, and you have all the algebra concerned with it. So Klebsch began this process, and people made fun of him. Prim famously said that there was really no point in trying to use algebra to fix function theory, because algebra should come from function theory, not the reverse. But Klebsch was very charismatic, and he developed a school of followers. And Brill and Noether, when Klebsch died young, Riemann died young, Rock died young. This is a period with lots of disease and trouble. But Klebsch was succeeded by Brill and Noether, Max Noether, Emmy Noether's father. And they, with Macaulay actually, carried forward the process that Riemann had started. Now I want to use the Riemann-Roch theorem, so let me state it for you in a slightly special case, but really almost the general case. So Riemann-Roch says that if you have a Riemann surface, well, what does a Riemann surface look like? This, if we could draw all the complex points, would be a Riemann surface of genus 3. So that's something like this. That's supposed to represent a torus with 3 holes, if you like, or a surface with 3 holes. And the Riemann-Roch says, so this is genus 3. And Riemann-Roch says that if you have such a surface and a point on it, so let's say we have a point P in this surface, and you look at the functions with poles of order bounded by a certain number n at P. So you should understand first that there are no holomorphic functions on this thing. That's one of the central facts about the field, because a complex analytic function takes on its maximum on the boundary of a disk. And so if you have a compact surface, if you had a complex analytic function everywhere defined, it would have a maximum somewhere, but then the maximum would have to be on the boundary, and slowly the maximum would be everywhere. So only the constant functions are defined everywhere here. But if you remove a point, then you might have lots of functions, but they'll have poles at that point. And you can say the dimension of the space of functions, meromorphic functions, that is, functions on X, let's call this surface X, with poles of order less than or equal to n at P. That's always a finite dimensional space, it turns out. And if you add to that, this is Riemann-Roch, if you add to that the number of differential forms, global differential forms, there are nowhere meromorphic, everywhere holomorphic differential forms on this surface, in fact, the G-dimensional family of them. And if you add to that the dimension of the set of holomorphic forms, differential forms, on X with a 0 of at least order n at P, vanishing to order at least n at p, then that sum, right, the sum of these two funny dimensions is always equal to n plus 1 minus g. That's the Riemann-Roch theorem. The general case, you replace one point with a divisor, a multiple of one point with a divisor, and you have the general case of the theorem for curves. Of course, this has been generalized and generalized. Unfortunately, as the dimension goes up, the utility of the theorem goes down, more or less inversely with the dimension. But nevertheless, for surfaces, it's still quite useful. For curves, it's the philosopher's stone. You can do anything with Riemann-Roch, and we will in a moment. But for surfaces, it's still useful. For higher dimensions, less and less so. It's really an Euler characteristic, which is equal to this. And the Euler characteristic has more and more terms in it, which is why it's not so useful afterwards. Anyway, that's the theorem. And this was studied a lot at the time. And Weierstrass, so this is 1857 and 1860. So this, there's an inequality. If you leave out this term, you get an inequality, and that's Riemann in 1857, and then Roch contribution was in 1860. Is that the right date right now? 1865, sorry. So among other people interested in this was Weierstrass, and he lectured on function theory in the 1860s, and he proved what's now called the Lückensatz, the theorem of the gaps, and that is the nice statement that if you pick a point, there's my point, and you look at the functions which are everywhere holomorphic except at that point, and have maybe a pole at that point, then they have certain order poles, but they don't, not every order is taken on. Why should it be? But if you count the number of orders of poles which are not taken on, the gaps, then you always get exactly G gaps. So Weierstrass theorem. So if you say S is the set of orders of poles of functions, orders of poles at this point P, of functions holomorphic away from P, then S contains all the the non-negative integers, except for exactly G. So this is equal to the non-negative integers minus some set G, let's say, and the cardinality of the set of gaps, it's called, is always exactly the genus. So that is actually an immediate consequence of Riemann-Roch. I don't think that Weierstrass had proved it in such an easy way, but we don't know because he didn't publish his theorem. It was finally published in 1875 by his student, Schottky, in 1875. But it's easy to see from Riemann-Roch, so let me prove it for you. If I think of passing from n times the point to n plus 1 times the point, this number obviously goes up by 1. So this number might go up by 1, or this number might go down by 1, but not both. So what does it mean for this number to go down by 1? It means there was a function vanishing to order differential form vanishing to order exactly n. And you've left that out when you decrease n by 1. On the other hand, what does it mean for this number to go up by 1? It means that you get an extra function when you get to n plus 1. So there's an extra function. So either there's an extra function and n plus 1 is a vanishing order, or n is an order you get an extra pole order, or n is an order of vanishing. So that says that the set of vanishing orders of differential forms is exactly one off from the set of pole orders. So G is equal to the set of n such that there exists a differential form vanishing to order n minus 1. Right? That's what the Riemann-Roch theorem says when you untangle it. So, well, how many different orders could there be differential forms vanishing to? This is a G-dimensional family of forms. If you can sort them by the order of vanishing, if you have two that vanish to the same order, you could take a linear combination and get one that vanishes to one higher order. So the number of different vanishing orders is the dimension of the space of holomorphic differential forms, and that's G by definition. So number of vanishing orders is equal to the dimension of the space of holomorphic differential forms. And that's G. So that proves the Weierstrass gap theorem. We can see that actually on this example. Here's a Riemann surface of genus 3. And how do we see the differentials? That's not quite so obvious, but a fairly easy argument from Riemann-Roch shows that the divisors of differential forms, the set of vanishing, the points where the differential forms vanish, are exactly the sets where a line cuts the curve. So here's a, let's say my point is this one. Then I have a differential form vanishing, well, to order 0 if I draw the line not through the point. Here's a line that meets the curve once. Here's a line that meets it twice. So my vanishing orders in this case are 0, 1, and 2. And therefore the gaps are 1, 2, and 3. So let's make a little chart. In fact, maybe I said enough about Riemann-Roch that you don't want to see it anymore. So do it here. So if we have orders of vanishing, that's my set of differential forms. If I have orders of vanishing 0, 1, 2, and you can see that at most points that will be the case, right? This was a non-special point in some way. 0, 1, 2. Then the gap sequence is 1, 2, 3. And and S, the set of orders of poles, that's the complement of the gap. Well, this has a little more structure, which you should be aware of. If I multiply two functions together, if they have poles at P, then the pole orders add. They look like 1 over z to the n and 1 over z to the m. The product is 1 over z to the n plus m. So pole orders add. So the complement of the gaps, the set of vanishing of pole orders, is actually a semigroup. In this case, 0, and then I skip 1, 2, and 3, and I get 4, 5, 6, 7, etc. Right? So that's the semigroup of this point. That's the ordinary point. But you can see there are some points which are flexes, right? Here's a point, not very well drawn, where the line meets the curve three times instead of two times. So then I would have vanishing orders 0, 1, always as a 1, and 3. And the gaps then would be 1, 2, and 4. And the semigroup would be 0, 3, not a gap, 5, 6, of course, is there because it's twice 3. So, but I'll put it in anyway, 7, 8, 3 plus 5, but we can put it in 9, etc. Okay, so that's the semigroup. And now there might be one more kind of point that would be interesting. There might be a hyperflex. A flex point is a point where the tangent meets the curve 3 times instead of 2 times. Hyperflex, it meets it 4 times. So we might have a point with 0, 1, 4. And then the gaps would, of course, be 1, 2, and 5. And the semigroup would be 0, now 3, 4. And everything else. We skip 5, but 6 is there, 7, 8, etc. Right? So those are the possible semigroups. Now you might say, what if I had 0, 2, 4? Because that's another way to have a semigroup with 3 gaps, right? We're supposed to be looking at all semigroups with 3 gaps. What else could there be in a semigroup with 3 gaps? Certainly I could have a semigroup that looks like 0 is always there, 2, 4, 6, right? Then 1 is a gap, 3 is a gap, 5 is a gap, and then everything else. That's a semigroup with 3 gaps too. That's another semigroup. The number of gaps is now called the genus of the semigroup universally. So I'll use that terminology. These are all the semigroups with 3 gaps, by the way. There's nothing else. Where did this one go? You can't have a smooth curve like that because that would mean a line would meet the curve 3 times, right? This would correspond to 0. Did I do this wrong? No, that's right. 0, 1. No, there should be no 1 here. That's the semigroup. What is wrong with my calculation? So it's the vanishing orders. I'm writing down the wrong place, that's all. So I could have vanishing orders 0, 2, 4. And then the semigroup would be 1. No, can't have 1. The gaps would be 1, 3, 5. That's right. Okay. The gaps would be 1, 3, and 5. And then everything else is in there. I have 3 gaps, 6, right? And the semigroup is everything else. 0, 2, 4, 6, 7, I guess. 8, everything else. That's right. So what happened to this case? This is the case where I have a function of order 2. It can't be a smooth curve. This would be a double point of the curve, at the cusp actually. But what it can be is a double covering of P1. So these are the hyperelliptic curves, if you've heard of that. They don't embed in P2 at all. But every other curve of genus 3 has a smooth plane quartic model. So we've caught all the curves now and all the possible gap sequences for a semigroup of genus 3. Any questions about this? This is the most concrete example you're going to get. So if you have any questions, this is a good time to ask. Now, this was a important theorem, important application of Riemann-Roch. So people were interested, and Hurwitz got into the story and asked, in 1892, does every semigroup appear? Numerical, these are called numerical semigroups. Semigroup appear. So take a semigroup with G gaps. Is there a Riemann surface and a point on it with that semigroup? Sorry? Additive semigroup. So if you take two polar orders and multiply the functions, you get the sum of polars. These are additive semigroups. Semigroups in N and missing exactly G if you want that. So how many semigroups are there of genus G? That's an amusing story in itself. By the way, the literature on numerical semigroups is vast. It's a whole branch of mathematics that not so many people know. It's really combinatorics. And there are lots and lots of open combinatorial questions. But one thing that people do know is that the number of semigroups of genus G is asymptotic to 1 plus the square root of 5 over 2 to the gth power. Why the golden ratio appears, mystery to me, but that's the truth. So it grows exponentially, but it's not even known that when you go from G to G plus 1, the number increases always. So lots of mysteries like that. If you're looking for combinatorial problems, open any book on semigroups and you'll find more than you wanted. Anyway, there are not too many semigroups of a given genus, and you can ask whether they all appear. And this was, well, Hurwitz was, of course, a well-known person at the time, and so people paid attention, and the answers came quickly. So a Frenchman named Hoare, 1896, gave necessary conditions and said that not every semigroup occurs. But then Hensel and Landsberg proved that every semigroup occurs. So there the matter seems to have rested for quite a long time. I don't know what provoked it exactly, but I think it was the really the beginnings of deformation theory that started this. And Henry Pinkham, who was a student of David Mumford, in 1974 took what in some ways is the next step and interpreted this as a deformation problem. So Pinkham's theorem says take a very singular curve, take the curve defined by the semigroup itself. So you can take the semigroup ring, let's call it R sub S, is equal to K. Take your favorite field, maybe minus the complex numbers, and look at all the T to the little s, such that little s is in S. Okay? That's a ring. It's a subring of the polynomial ring in one variable. Rather innocent one-dimensional ring. And but it's certainly a very singular curve. If you think of this as a plane curve, the case that you all know is the case when the semigroup is generated by 2 and 3. that's an ordinary cusp, right? So these singularities look like very complicated cusp singularities. And Pinkham said that the semigroup S will appear as the semigroup on a Riemann surface, a Weierstrass semigroup it's now called, if and only if this singular curve can be smoothed, keeping the grading. So this is graded by the positive numbers, or by S, if you like. So the theorem says S is a Weierstrass semigroup in the sense that it appears at some point on some Riemann surface somewhere, if and only if R sub S admits a graded smoothing, can be smoothed in a flat family, that is to say, keeping the grading. So Pinkham thought of this as the way to do this is obviously to take the versatile deformation and see whether the generic fiber is smooth. And he used that idea to prove that all semigroups of genus 3 and 4 occur. Not so hard. But it turns out that you can do other kinds of smoothing too. So the next thing that happened actually didn't depend on Pinkham's theorem. It depended on the existence of small personal computers. And Ragnar Buchweitz, when he was a postdoc with me actually at Brandeis, though I had nothing to do with this, programmed his computer to look for semigroups that would exhibit a certain obvious obstruction to being a Weierstrass semigroup. So what's the obvious obstruction that Buchweitz used? If you have a Weierstrass semigroup, it has a certain number of gaps, and that corresponds to the vanishing orders, as we've seen, of differential forms. If you take the set of gaps and add it to itself, then you get at least some of the vanishing orders of quadratic differential forms. Because if you have differential forms that vanish to order A and vanish to order B, you multiply the functions that define them, vanishes to order A plus B. So you get some gaps of quadratic differential forms. So, and Riemann Roch tells you the number of quadratic differential forms. So the dimension of omega tensor omega, the dimension of the global sections really of this sheaf, if I wanted to be precise, is by Riemann Roch, which I've unfortunately erased, just 3g minus 3. This is an easy computation. It's the degree of this, which is twice the degree of omega. The degree of omega is 2g minus 2. So 4g minus 4 plus 1 minus g is 3g minus 3. And if you have a genuine Weierstrass semigroup, then the set of gaps, which corresponds to these vanishing orders, when added to itself, should not have more than that number of elements. So Buchweitz's basic program ran overnight, looking what one semigroup at a time, all the semigroups that he could construct, and it got to genus 16 and found one. So Buchweitz actually writes down a semigroup which fails this test, and I'll write it down for you. Not very illuminating, but interesting that one can do it so very concretely. There it is. So the basic computer in the morning had the following semigroup: 13, 14, up to 18. And then 20, 22, and 23. So the semigroup generated by those numbers, right? You get big numbers now, which has 16 gaps. You can count them. 1 up to 12 are gaps. That's 12 gaps. Then you get a gap here, 13, 14, and there are 2 more out here, 15 and 16. I'm sorry? 13, 14, no, there are 3 dots there that you can't see. All the numbers between 13 and 18 are in the semigroup. Maybe I should have written them down, but anyway. So it's an interval, 13 to 18, and then these 3 numbers. And there are 16 gaps. Genus is 16. So, well, okay. And if you add it to itself, instead of getting 45, 3 times 16, 30, 18, 48 minus 3, 45, you get 46 numbers. So if you take the set of gaps, G, which is 1 up to 12, and etc., and then G plus G, and you just look, the number of things in G plus G is 46, which is greater than 45. So that's an incontrovertible counterexample to the theorem that Hensel and Landsberg had proven. I lectured on this example in front of an audience that contained a real expert on the subject a year or so after, and he said, no, this can't be right. Hensel Landsberg proved that every semigroup occurs. So this was a rather influential text. This was the basic German textbook of the time. Why should you doubt what was in it? But it was wrong. Well, okay, so not every semigroup occurs. So this started lots of work to find more examples. You can, if you have a bigger computer, you can find more of these in larger genus. You can look at M Buchweit semigroups, where you have to add the gaps M times before you get a counterexample. And so there was a whole industry of producing more counterexamples, more examples of non-Weierstrass semigroups. But nobody could find one of genus less than 16. So it became an interesting question. Is every semigroup of genus up to 15 actually a Weierstrass semigroup? Well, various people found other kinds of counterexamples. You might try to simplify things in different ways. The minimal generator in a semigroup is called the multiplicity. It is the multiplicity of that singular curve. So multiplicity of M, multiplicity of S is the minimum positive element of S. S always contains 0 positive element in S. And Buchweit's multiplicity was 13, so it became a question, is there one less than 13? Is there a semigroup of genus less than 16? And a Japanese mathematician named Komeda very proudly found one with multiplicity 8. Exists one with multiplicity 8, but the genus was rather big. The smallest genus he could get was 34 that way. And so I became entranced with numerical semigroups a couple of years ago after hearing a very beautiful exposition by a combinatorialist named Christopher O'Neill. And there's a lot of depth to this subject, which I had never realized before. But Frank Schreier and I then set out to prove that all the semigroups up to genus 15 would occur. So how do you prove that a semigroup actually occurs? Pinkham's method is the only one that I know, other than drawing pictures on the blackboard in very small cases. And so you might ask, can you really make a family of smoothings? Pinkham's theorem, by the way, is not trivial at all, but there is but one direction, which is the more interesting one for us, I guess, is very easy. If you have a Weierstrass semigroup, if you have a point on a Riemann surface, which is Weierstrass with a certain semigroup, then you can get from that a smoothing family of the semigroup ring. So let me show you how that works. So this is the easy part of Pinkham's theorem. Easy Pinkham. So suppose you have P in X, a Riemann surface of genus G, and you want to, and it has a certain Weierstrass semigroup, semigroup S, and you want to turn that into a smoothing of a family of curves. So X is a lousy curve to think about because there are no functions, right? But if you remove P, one of the many consequences of Riemann rock is that if you remove any point from a Riemann surface, it becomes an affine curve. So we remove P, we get an affine curve. It has an affine coordinate ring, lots of functions. Let's say A is the affine coordinate ring. Of X minus P. Then you can filter A by the order of pole of a function at P, right? Every function in A except the constant functions has to have a non-trivial pole at P because there are no everywhere holomorphic functions. So you can take set A sub I is equal to the set of F in A such that the pole of F at P, if you extend it, is order less than or equal to I. So this is an increasing filtration of A. The union is all of A. So you can make it, and this is a very standard bit of commutative algebra, you can make a family of algebras out of that by taking A plus T times A0. A0 is the set of functions with no poles at P. That's the constant functions, right? So A0 is K, the ground field, or C if you like, plus T times A1 plus T squared times A2, etc. These are direct sums. So this is a K of T algebra. Let's call it A tilde. A K of T algebra. It's in fact a subset of A of T in an obvious way. Because it's a subset of A of T, and A was the this affine ring of a nice irreducible reduced variety. A is a domain, so A of T is a domain. So this thing is T torsion free. So that means that it's flat over K of T, nice flat family. If I tensor it with, if I throw in T inverse, if I just, or tensor it with a quotient field, but if I put in T inverse, then I can have T squared times T to the minus 1 here. That'll be a T power. So I get T2 here. I also get T3, T4, T5. So I just get A0 tensored with well, all of A, right? I get A tilde tensored with K of TT inverse over K of T is A of TT inverse, or A tensored K of TT inverse, I guess I should write it. So generically, it's just A, but when I factor out T, what happens? I have A1 mod the constants, so those are all the functions with poles of order exactly 1, plus A2 mod things of poles of order A1. So I get exactly the semigroup ring. So A tilde tensor K of T mod T is R sub S. So this is a flat family of curves with the generic fiber smooth. It's just the affine, it's just the Riemann surface minus the point. And everything is graded properly. So this shows that if you have a flat family, or if you have a Riemann surface and a point with a given semigroup, then you can make a flat family, and the semigroup will appear at the point at infinity on your Riemann surface if you then complete the Riemann surface, complete this smooth thing to a compact surface. So that's half of Pinkham's theorem. So it seems natural, if you want to prove that a semigroup does occur, to actually write down the semigroup ring and try to smooth it. The versatile deformation is one way, but there are lots of other ways too. So Harris and I proved that a certain number of semigroups really do appear. In 74, I think. What is the actual date? In the 80s, I guess. So myself and Joe Harris proved that a lot of semigroups occur in a different way. You can take a curve, Riemann surface of genus G minus 1 and add and find a Weierstrass point that you like, and then add an elliptic curve. So this is genus 1. This union is a pretty nice curve, not smooth, but pretty nice, of genus G. And if you take a point here, which differs from this point by a certain torsion, and then smooth this thing to a smooth curve, and that's always possible, because this is such a simple singularity, then you get a Weierstrass point, which you can compute of genus G. So we smoothed these things and produced some Weierstrass points. I won't write down the exact condition because I want to show you a different construction. A student of Joe's named Pflüger then improved our method a bit using the same approach. These are called limit linear series that we have. So Pflüger improved this and proved some more things were there. So that gives various pretty big family of Weierstrass semigroups that were known to exist for real, but by far not all of the semigroups up to genus 15. So Frank and I decided we would try to prove everything up to genus 15 occurred by actually producing flat families. So starting with this semigroup ring, RS, we wrote down not the versatile deformation, but a universal unfolding. Some of you know what that is. You add all the possible terms that you could have and still have a graded family. And then inside that, you look for the flat subfamilies, which is an equational thing. The computers can do this, it turns out. And Macaulay 2 is the tool we used, though there are probably other ways too. And we got up to genus 10. So every semigroup up to genus 10 really does occur. But then the computations just become too hard. So it's now known that every semigroup of genus up to 10 occurs. It's a brutal computation, but it works that far. And we were able to do all but a few cases in genus 11, but it gets beyond what our computers can do, even letting them run for a week or two. So I think it's hopeless to do by brute force up to genus 15. On the other hand, we also found an example of genus 13, which is not Weierstrass. And the example is much simpler to write down than any of the things I told you before. The semigroup is generated by the numbers 6, 9, 13, and 16. So the multiplicity is the lowest known, 6. By the way, everything up to multiplicity 5 is Weierstrass, so 6 is the first possible candidate. And genus 13. And I want to describe to you how we found this. And it turns out that you can also write down 6, 9, G, and G plus 3. And for G at least 13 and not divisible by 3, this is also a non-Weierstrass semigroup of genus G. And experimentally, we can fill in all the ones where G is divisible by 3 too. You can see why G has to be not divisible by 3. If G were divisible by 3, then all these numbers would be divisible by 3, and every element of the semigroup would be divisible by 3. So it's not, doesn't have a finite complement. But when G is not divisible by 3, it does have G elements in the complement, turns out. So how was this found? Frank and I both are addicts, I would say, to Macaulay 2. I've often said that that's the only computer game that I've ever been addicted to. And so we were playing with semigroups and unfoldings and looking at them, and it was natural to us then to look at the syzygies of the semigroup rings. And I'll tell you about the syzygies of this particular semigroup ring. I think this example has done its part. Now, if you think about how you might expect to come upon a non-Weierstrass semigroup, you should think of this universal unfolding. So you have a big family of things that are deformations of the semigroup ring, and they're all supposed to be singular. So how would that happen? Certainly the central fiber, the semigroup ring, is very singular at one point. Everything else is smooth. As you deform, if everything is going to be singular, then you should expect to see a section of your family. You've just followed the singular point. Well, maybe it splits into 17 singular points. There might be a multi-section. But there should be a section or a multi-section that you can see. And that's what we saw when we looked at the syzygies. So if you take this semigroup, S, as I say, 6, 9, 13, 16, and you write down the semigroup ring, RS, then it's a homomorphic image of a polynomial ring in 4 variables. P, let's call it. P is maybe C of x0 up to x3. Not quite a plane curve, but a space curve, if you like. And then it turns out, you just write it down on the computer, that there are exactly 6 equations, p to the 6th, and 8 relations on those, and 3 relations on those. Now, we looked at a lot of examples, and we tried to understand what we were seeing. This particular example, the last matrix, so it's an 8 by 3 matrix, 3 columns. The first column was rather remarkable. It had the 4 variables in it, x0, x1, x2, x3, and then zeros. Well, why should that be interesting? Let me try to convince you that that's a section. You're looking at a potential section of the family. At least you need to know that if you smooth this thing, then those zeros stay. That's what you need. Now, when you smooth in a flat family, I should say the shape of the resolution stays the same. All the gradings stay the same. The numbers of syzygies, etc., stay the same. So this is the picture of the deformation as well as of the semigroup ring itself. But who's to say that those zeros stay 0? Well, one reason for them to stay 0 would be for them to have negative degree, right? Every element of each of these matrices has an effective degree. If you think that everything is homogeneous, so the column degree plus the degree of the entry has to be the row degree. The row degree is a degree here, the column degree is here. And so it turned out in this example that these have strictly negative degree. Now, if something has negative degree and you make a graded deformation, it still has negative degree. There are no functions there. So the zeros remain. Why is that useful? Well, here you have 4 elements. They define, of course, the singular point of the singular curve. But also, even if you make a deformation, those 4 elements generate an ideal which must contain the ideal of the deformed semigroup. That's because the dual of this matrix is a presentation for the canonical module of the curve, and the annihilator of the canonical module is the same as the annihilator of the ring, the same as the ideal. 4 elements generating an ideal. Well, these elements then are the elements of a quotient of the first generator of the canonical module into the submodule generated by the other 2. That quotient must contain the annihilator. So these 4 elements will contain the annihilator. Also, 4 elements are containing an ideal, a prime ideal with 6 elements. So they must have strictly larger codimension. This prime ideal has codimension 3, so these have codimension 4. So this is a regular sequence in every deformation. And it's a regular sequence which defines a section globally. Now, why would there be a section unless there was a singular point? Right? That was our feeling at that moment. You know, what else? What other reason could there be to have a section that extends the origin? And indeed, this is more complicated, so I won't do it. But if you trace through and look at the rest of the resolution, it turns out that this is the tail of a resolution of 4 of the 6 generators. And those 4 stay inside the square of this section ideal. And that's enough to make all the fibers of any deformation, singular. So at this point. So this is the signature, in a way, of a non-Weierstrass semigroup in this case. And it turns out that this is quite common. We found lots and lots of other examples with this form of syzygies and this kind of a section. I don't know why it should be common, but it turns out to be. And so there are lots of semigroups out there. You might ask then, what's the balance, right? We started with Hurwitz's question. Well, okay, not everything occurs. How much do we know? If you tot up all the ways that people have proved things are Weierstrass semigroups, you get, and you know asymptotically the number of semigroups of genus G, you get 0%. How about the non-Weierstrass semigroups? Also 0%. So basically, we know nothing about Hurwitz's question to this day. And there it remains. So thanks for listening.
Any questions or comments? Alberto?
How do Weierstrass points behave under holomorphic coverings?
Under what?
Holomorphic coverings. That you know, any Riemann surface of genus 2 is
Yes.
Any surface covers a surface.
Right. So people have studied that a lot, actually, as a way of constructing non-Weierstrass and Weierstrass semigroups. So if you take a semigroup and take just the even numbers and divide by 2, you get a new semigroup. And it turns out that that's the picture of a double covering. So that's something that has been done by Torres, starting, and then Komeda, whom I mentioned. And so this is a very good question, a very fruitful way of producing
Every
examples.
semigroup appears for a larger genus because you take a covering. My question is, what is the semigroup corresponding to a covering?
Right, so it's pretty, so far,
you told me, but you didn't get it very well.
pretty rare, but special semigroups. You can, from some semigroups that you know, you can produce others that appear. But for large genus, I think my guess would be that fewer and fewer semigroups actually appear. I don't know, but plausible at least, yeah.
And one last question, I mean, for people that don't work in algebraic geometry, Weierstrass points are sort of mysterious because you think that a Riemann surface is democratic, all points are equal, and that's false because there are some special points.
That's right.
And somebody explained to me why, if you take the Abel-Jacobi embedding of Riemann surface into the Jacobian, the image has a non-positive curvature by your output, and the points where the curvature is 0 is precisely the points.
I see.
So it's, I don't know, you cannot do anything with it. You need algebra, I know, but at least you see why there are special points.
You can see it another way too, which is closer to the algebra and closer actually to the example I drew. If you take this thing, then the number of the Weierstrass points are the flex points. And the number of flex points is the intersection with the Hessian. So it's the quartic equation. The Hessian is a 3x3 matrix of quadratic forms, degree 6.
The Hessian is the curvature.
Right, that's right. So there are 24 Weierstrass points on this thing counted with multiplicity. And in general, there are G cubed minus G Weierstrass points on every Riemann surface counted with multiplicity. And they're enough to rigidify the surface. So any automorphism that fixes all the Weierstrass points must fix the surface, point-wise. So they're important landmarks. I mean, if you draw the surface this way, right, you don't see any special points. And of course you can't because they depend on the analytic structure. They're a 3G minus 3 family of these things, 6-dimensional family of those. So you can't tell where the Weierstrass points are going to be in advance.
Thank you.
Yeah.
You said that you tried to push the computations beyond the number 10,
Yes.
and you ran into problems. Can you tell us what the bottleneck is at this point?
So you're dealing with polynomial rings with a large number of coefficients. So what do you have to do the universal unfolding? You take the equations and then you add every possible term of lower degree multiplied by a new variable of a degree that fixes the degrees so that the degree is constant. So if you have lots of equations of high degree, then you have an enormous number of new variables. Then, so okay, that's no problem. You have this big family, but now you have to find the flattening relations. So the flattening relations are exactly what it takes to lift the syzygies. So you write down your deformed equations and the deformed matrix here, and you see if the composition is 0. Might be 0, might not be. If it's 0, then things are flat and you're happy. If it isn't 0, then you have to put in the new composition as a new relation. So you get a lot of relations that way. Computing, so you have then, so you now maybe you succeed, you have a flat family, but it still has a lot of variables. So you want to reduce the number of variables because now we have to choose a random point and check whether the fiber is non-singular. And so reducing the number of variables is the first order of business. And so it turns out that not all the things you added are really necessary. Finally, there'll be a one-parameter family, which is a smoothing. So you don't need all those bothersome variables. You only need some linear combination, one linear combination of them. So you might try to first eliminate as many variables as you can and still have a family with a non-singular fiber. If you're right, so first you test the general thing. If it has only a singular fiber, of course, you're done. But otherwise, we're proving things are Weierstrass, you have to find a non-singular fiber. So you find a non-singular fiber, then you try to reduce the size of the family to get one in the flat family. And there are just too many variables, I guess, is the quick answer to your question. So we can make the computation, we can write the code, but it just doesn't finish in any time that we've been willing to wait so far. And memory is also a problem. So time and memory, as usual.
Okay, thank you.
These are Grosvenor basis computations of a big kind. Yeah.
I have another question, at least for pedagogical purposes. Has anybody checked the purported proof of Hensel-Landsberg and find out what the error is? It should be something like it's obvious, something like this, yeah?
It must be, yes.
Yeah.
So I confess that I'm not a good scholar in this. I have not checked either Hoare's paper or Hensel-Landsberg, but I at least have an excuse for the second one. I requested Hensel-Landsberg from deep storage in the Berkeley library system, and it just arrived while I'm away. So I will get to look at it when I get home. I wondered whether you might have Hensel-Landsberg here in the library, but probably not. 1902, I think.
I suppose there's another question. Yep. Yeah.
Not divisible by 3. What if the genus is 11 or 12, or even the genus is greater than equal 13, but divisible by 3? Can one say something when the genus is 11, 12, or not divisible by 3?
So we know nothing about genus 11 and 12, positive or negative. Divisible by 3 doesn't seem to be a problem. We're just not smart enough to guess the pattern of numbers that we need. so far. In fact, I have a collaboration with a man named Sergei Gukov, who's an expert on machine learning, because neural networks are good at guessing patterns. And so I presume we'll have every genus finally, but experimentally we can do every genus up into 300 or so by just random choices of 4-generator semigroups that happen by accident to have this kind of resolution. So, so every indication is that every genus bigger than 13 will have non-Weierstrass semigroups. How many, we don't know. These are very special.
Are there more questions? Oh, thank the speaker again. Thank you very much for the talk. Go ahead, man. Yeah. Thank you very much for your care.